Hi, I'm Shell from ASU, and in this talk, I will demonstrate our framework for designing efficient machine learning accelerators in minutes. Machine learning models have enabled automation and intelligence in variety of applications, including computer vision, language processing, recommendations, scientific computing, and gaming. And ML is being used from cloud to edge and IoT. So industry has been developing NPUs or accelerators for machine learning. Lot of work is in designing suitable NPU for the target application. And the tables in the slide, they just show the range of designs and design constraints. For example, a cloud accelerator could have petabytes of memory and hundreds of watts of power, and mobile NPU may only have a few GB of memory and few watts of power budget and cost $100. So designing an appropriate accelerator is not just important for low cost or smooth processing for users, but it is also important from the energy and sustainability perspective. A recent paper from Facebook showed that most of the carbon footprint is in the manufacturing. So the time and energy of humans that is used to design the accelerator, the computing that is used, it's very important. So we advocate for DSE framework that not just result in efficient accelerator, but it is agile, that is, it takes less time. Even with modest options for the parameters of hardware, for example, power of two values, solutions can range from millions to quadrillions. And even for every hardware design, valid software solutions like mappings can be billions. So the collective space is vast. And the search space explodes further when exploring accelerator model codesigns, further heterogeneity and specialization like sparsity or multi-accelerator designs. And given the vast space, the exploration must not just yield feasible and efficient solution, but also be quick for dynamic exploration and sustainability. Current DSE frameworks, they use black box approaches like Bayesian optimization, reinforcement learning, random search, or genetic algorithm, and they are inefficient because they don't reason about why explode configuration could lead to high cost. And they may be even unaware of the constraints, whether they are even met. So even after taking days, they may not find valid solution or may obtain inefficient solutions. Since they take thousands of trials, they are less sustainable and cannot be used for dynamic exploration, which is essential to figure out right hardware-software configuration before deployment. For example, before deploying a new machine learning model on end-user FPGA. Or same is true when scheduling for hubbub detection or traffic detection on some of the nodes of reconfigurable edge infrastructure. Our DSE framework can effectively do hardware-software co-designs, and so it can find order of magnitude efficient solutions. And it does so in minutes instead of taking days. And here there are two key insights. One is that it focuses more on finding valid solutions in the vast space. And second, it strives to improve objective at every iteration by removing bottlenecks behind high costs. So it can achieve efficient solutions quickly. And so now we show how to use our DSE framework. Designer need to specify DSE technique, the DNN model, data flow optimization technique, and so forth. And for data flow optimization, we use our Maze Runner framework. And this command here shows just a shortened version of the actual command. And the actual command actually allows specify more options and details like for constraints, objectives, design space file, and so forth. And now we can run the exploration for questions and answers with the BERT language processing model. And it has 361 layers. So we can see that here framework chooses one hardware configuration and it optimizes DNN layers, layer-wise, And then after exploring some candidate, it chooses best solution that it is valid and efficient. And for the selected configuration, it would find the bottleneck behind the high cost and then optimizes hardware configuration to reduce the cost. And then the process repeats. So once this finishes, you can see that it should be able to find efficient solutions quickly, for example, in minutes. For example, you can see here that it finds efficient solution in just 1 minute and 20 seconds. And likewise, we found that our DSE framework can optimize latency of computer vision models by order of magnitude compared to previous DSE frameworks. So they can enable high throughput computer vision at the edge. Thank you, and I hope you enjoyed this talk, and I'm looking forward to more discussions with you at the upcoming conference. Thank you.